The Uniline division of Robert Shaw Controls Company is pleased to bring you this video presentation on the fundamentals of pneumatic control systems. The previous sections of our Fundamentals of Pneumatics video covered the air supply and control devices. Now that we have covered the source of clean, dry, and oil-free air and are able to choose the final control devices required, we will now discuss the function of the pneumatic controllers that are required to make the system function properly. The controller is a device that senses a condition and takes an action based on a change in that condition. This sensed condition may be temperature, pressure, or humidity. The controller provides an output signal based on that sensed condition. If the medium that is being sensed is controlled by the controlling device, then this medium is referred to as the controlled variable. The controller's output signal is called the branch line signal or branch pressure. This branch line signal operates a control device, which will, in turn, change the condition of the controlled variable. This controlled variable may be the temperature or static pressure of air in a duct, the temperature or pressure of a fluid in a pipe, or the control of humidity or temperature in a space. The output signal or branch line signal is a 3 to 15 psig pressure, which is linear in relation to a change in the sensed variable. The controller receives a main air supply pressure. Most devices operate with a 20 psig main air supply, though this may vary depending on manufacturer or application. The controller varies the branch output to the final control device between 0 and main air pressure. The most linear portion of this signal is from 3 to 15 psig. Therefore, this portion of the signal is used for control. The operation of a controller to be used for a given application depends upon the action desired. Controllers may be either direct acting or reverse acting, and in some cases, may have the capability of being converted from one action to another. The direct acting controller varies its branch line pressure in direct relation to a change in the sensed variable. In this particular example, the temperature controller is sensing an increase in temperature and will increase its branch line pressure. A decrease in temperature would create a decrease in branch line pressure. A reverse-acting controller provides an output with an inverse reaction to a change in the sensed variable. A fall in sensed temperature would provide an increase in branch line pressure, and an increase in sensed temperature would create a drop in branch line pressure. The controller output is a 3 to 15 psig signal generated over a specific range of the sensed variable. This specific range is referred to as the throttling range of the controller, also called the proportional band. The term throttling range is referred to by some manufacturers as sensitivity. There is a direct correlation between throttling range and sensitivity. Dividing the output range, 12 psig, by the throttling range yields the psig change, or sensitivity per degree of change, in the controlled variable. This room thermostat is a direct acting device and has a throttling range of 4 degrees. We have a given set point of 70 degrees. At an ambient temperature of 70 degrees in the space, the branch line pressure will be 9 psig, or the midpoint between 3 and 15 psig. Here we have a change in temperature with the temperature falling to 68 degrees. At 68 degrees, or 2 degrees less than the set point, our branch line output pressure would change to 3 psig. If the temperature in the space begins to increase, our branch pressure will also increase. As the temperature rises to 70 degrees, the branch returns to 9 psig. If the temperature in the space continues to rise to 72 degrees, the branch line pressure will rise to 15 pounds. This temperature change represents 2 degrees above and 2 degrees below the set point of 70 degrees. Thus, it is referred to as a 4-degree throttling range. Let's use another example with a throttling range of 10 degrees and a set point of 70 degrees. At set point, the branch pressure is equal to 9 psig. A 5-degree decrease in temperature will cause the output signal pressure to drop to 3 psig. A 5-degree increase from set point will cause the output pressure to increase to 15 psig. Another example would be narrowing the throttling range of this direct-acting controller to a 2-degree throttling range. In this case, the output pressure change of 12 psig will occur over a range of 2 degrees, yielding a 6-pound change per degree of temperature change, or a sensitivity of 6 pounds per degree. When setting the throttling range on a controller, the general rule of thumb is narrow enough for good control and wide enough to prevent hunting. Hunting is a condition that occurs when the controller overreacts to a change in the sensed condition, causing the controlled device to make drastic adjustments for small changes in the sensed variable. This condition causes the controlled variable to overshoot its set point in both directions, as shown in the graph. We have briefly touched on the use of a thermostat in our discussion about throttling ranges. The thermostat is the most common type of controller in the field because of its use in almost every zone within a pneumatic control system. There are 2 distinct types of pneumatic thermostats, the single pressure and the dual pressure models. The single pressure pneumatic thermostat operates on a constant main air pressure and is the most prevalent of the 2. There are 2 types of single pressure thermostats, the 1-pipe or bleed type thermostat and the 2-pipe or relay type device. Dual pressure thermostats fall into 2 categories, day-night and the summer-winter models. In a heating application, the day-night thermostat provides the ability to have night setback or temperature reduction during those times when the space is not occupied. This function is performed automatically by changing or indexing the main air pressure to the thermostat either upwards or downwards. The summer-winter thermostat provides changeover from heating to cooling or direct to reverse action by a change in the main air supply pressure. Let's discuss single pressure thermostats first, since they are more commonly found in the field. This example of a typical single pressure system will illustrate the piping needed. A single pressure reducing valve or pressure regulator is used to provide a constant pressure to the rest of the system, represented here by our typical zone thermostat and control device. Main air is distributed throughout the building to our typical zones. The 1-pipe thermostat uses a single air line from a thermostat to the final control device or actuator. This type of thermostat is referred to as a bleed type thermostat because the thermostat itself constantly bleeds air pressure to the atmosphere. The constant pressure main air supply is fed through a restrictor into the branch line between the actuator and the thermostat. An orifice in the restrictor limits the volume of air supplied to the thermostat and actuator. The thermostat opens or closes a bleed orifice to bleed off or build up pressure in the branch line to the control device as dictated by the space temperature. This is the back of a 1-pipe pneumatic thermostat showing the connection and an example of a restrictor T used in this type of application. The restriction in the T is located at the input port of the T, and the 2 output ports are common. The 2-pipe thermostat, on the other hand, has 2 connections directly to the thermostat. These connections are main air input and branch output. The branch output connection provides the branch line signal to the final control device or other devices in the system. This is a relay type device, which is able to provide a larger volume of air to the branch line and is able to move the actuator more quickly and in a more positive manner than the 1-pipe device. Maintaining a constant main air supply pressure when using 2-pipe devices is less critical because the output of the device does not depend on a fixed orifice size to provide its motive force. So far, we've talked about types, outputs, and the throttling ranges or sensitivity of thermostats. Now it's time to talk about the operation relating to specific devices and their applications in the field. Thermostats, like other controllers, come in both direct and reverse acting types. The selection of a given type of thermostat depends on the type of application where it is being used and the desired failure mode of the control system when a loss of air pressure is experienced. Here is a hot water heating application using a normally open valve controlling the hot water supply. Because the valve is normally open, the valve is open when there is no pressure in the branch line. A direct acting thermostat must be used. As the temperature in the space rises, the branch line pressure will increase, closing the normally open valve. Here's another way to achieve the same results in a different application. Take a typical VAV system with electric strip heaters for reheat. In this case, it would be unwise to have constant heat in the event of air supply failure. The solution is to use a reverse acting thermostat and a pneumatic to electric switch or PE switch. Strip heater controls are wired to the common and normally open contacts of the switch. A rise in branch line pressure will close those contacts, allowing the heaters to operate. As the temperature in the space increases, the branch line pressure falls, and the PE switch contacts would open, shutting off the strip heaters. Shown here is a two-pipe room thermostat, the 2212-118. One of its more prominent features is the set point adjustment and indicator. Note also a temperature scale on the face of the thermostat body, which can be read off the end of the set point adjustment. Settings can be made or changed without the cover being installed on the thermostat. This aids in calibrating the thermostat. On the thermostat body is a branch pressure tap, which is used with a gauge and branch tap adapter to read branch line pressure for thermostat calibration. The bimetal assembly on the thermostat senses ambient temperature changes and responds by producing changes in the branch output pressure. This bimetal assembly is very heat sensitive. Touching or even breathing on the assembly will produce a rapid change in branch line pressure and inaccurate readings. Be careful when attempting calibration of these devices. This is the throttling range adjustment slide. Most Robert Shaw pneumatic thermostats are adjustable from a 2 to 12 degree Fahrenheit throttling range. A normal factory setting is approximately 3 degrees of throttling range, which produces a 4 pSIG output change per degree of temperature change. The calibration screw provides the ability to change the set point of the thermostat, or calibration point, to match the ambient temperature as required. There are many different types of thermostat covers available for commercial applications. Most common of these is the blank cover with a concealed set point adjustment and a full dial model with thermometer and exposed set point adjustment. There are a number of other variations of thermostat covers that may be used to meet the requirements of a given application or the specifications of an architect or engineer designing the control system. There are many variations of thermostats available, and you've seen just a few, namely the two-pipe single pressure devices. This is the Uniline Pneumatic Controls Catalog. The catalog provides device specifications, typical piping, part numbers, and replacement listings for original equipment models, including the control action and parts included. Shown here is a model 2212-118, direct-acting, two-pipe room thermostat with the accessories that are packaged with each device. Mounting requirements may vary depending upon the type of thermostat being replaced. A data sheet is packaged with each one of our thermostats. The first page of the data sheet shows similar information to that found in the pneumatic catalog, and in addition shows the cover options and accessories available. Inside the data sheet are general instructions for mounting, calibration, and other typical information required for installation. Also shown are various mounting options for replacing competitive devices. Where a more permanent mounting is desired, options with pipe heads are available, either in a mortar joint or on a wall where copper may be specified for tubing connections. Shown here are some of the other accessory items that may be found or needed in the field, such as the pipe heads, drywall mounting brackets, and aspirating boxes. Another option available for replacement of thermostats is the thermostat unikit. This particular kit is designed for the serviceman doing general service work in buildings with a wide variety of thermostat installations. This package includes the thermostat with adjustable stops, a conversion kit which is designed to allow adaptation to most competitive pipe heads, and a thermostat cover kit with a full dial cover and a blank cover option. Pneumatic thermostats have been around for many years. Most manufacturers have produced several generations of devices utilizing different mounting methods. The 22022 Pneumatic Thermostat Conversion Kit is designed to allow the adaptation of Robert Shaw devices to most applications in the field with a minimum amount of trouble. Let's take a look at information on the data sheet provided with the kit to replace the most commonly encountered devices in the field. A parts breakdown is shown on the front page. Also shown is the option of utilizing the wall plate skirt to cover marks left by older, large devices. An example of this is illustrated on page 2 of the data sheet, showing the differences in the mounting bracket when used with the skirt and without the skirt. There are several common types of thermostats found in the field. Each one has unique installation requirements. Most of these devices are discussed in the data sheet. We will now cover the replacement of an old thermostat. First, read over the data sheet, selecting the information that best suits your conversion application. Next, remove the old thermostat and any bracket from the wall. Determine the appropriate fittings for connecting to the pipe head. If the fittings in the kit will not directly attach to the pipe head, then it will be necessary to cut off the old pipe head and connect directly to the tubing. Connect the 3/16" OD Tygothane tubing to the pipe head adapters or directly to the tubing. Check to see if the wall plate will cover any marks on the wall. If not, plan on using the wall plate skirt. Now, check to see how much clearance is needed to clear the pipe head. It may be necessary to use the wall plate skirt to get an extra 3/16" clearance. If the skirt isn't needed for added coverage or extra depth and is not required for appearance, then break off the outer tabs on the bracket as shown here. Using the screws provided, mount the bracket to the wall vertically and centered over the old pipe head. Install the bracket so the stamped word "up" is positioned in the upper left-hand corner. On installations where air lines are surface mounted, the bracket must be mounted perpendicular to the air lines, and the notches on the inside of the wall plate must be cut out. Pull the Tygothane tubing through the hole in the bracket. Using the countersunk holes and slots, fasten the wall plate to the bracket as shown. Make sure the word "up" on the wall plate is in the upper right-hand corner. Adjust the wall plate until it appears level, then tighten the screws. Cut the Tygothane tubing and attach the main air line to the port marked M on the thermostat. Attach the branch air line to the port marked B. Place the thermostat on the wall plate, taking care not to kink the Tygothane tubing when pushing it back inside the wall plate. Attach the thermostat to the wall plate using the screws provided. Adjust and calibrate the thermostat according to the instructions packaged with it. Calibration of the thermostat will be covered later on in this program. Place the cover on the thermostat. Secure it with counterclockwise turns of the Allen head screw, located at the bottom of the thermostat. Take this opportunity to stop the tape and answer the questions on this section in your study guide. Starting in 1974, the oil embargo and increasing energy costs created a new awareness of the need for more energy-efficient buildings. Various manufacturers created a number of different devices or modified others to meet these needs and the particular specifications that were generated. One of this type devices is the dead band thermostat. This thermostat differs from the standard pneumatic thermostat in that it has two set point adjustments. It is a single pressure device which offers separate heating and cooling set points and a single branch line output. This type of thermostat is used where an individual thermostat controls both the heating and cooling function. The throttling range of the thermostat is divided up or split between two set points. A dead band is created where no heating or cooling energy is used. The width of this dead band depends upon the heating and the cooling set points of the device. This graph shows the operation of a direct-acting dead band thermostat. As the temperature in the space rises, the branch line pressure of the thermostat rises proportionately until the space temperature reaches the dead band. The dead band output pressure is factory set for 7 psig, and a fixed 3-degree throttling range is split between the cooling and heating set points. This dead band output pressure is maintained until the temperature reaches the lower end of the cooling throttling range. As the temperature increases through the cooling throttling range, the branch line pressure will continue to increase proportionately. Another type of thermostat found in the field is the unit ventilator thermostat. This thermostat is designed to mount inside the cabinet of a unit ventilator. This Robert Shaw device utilizes a remote bimetal sensing element that is mounted in the return airstream. Some competitive models utilize a bulb and capillary arrangement to provide the same function. Shown here is a characterization of this type of application. A piece of 1/4-inch tubing is used to connect the remote sensor to the thermostat body. This allows for easy routing of the tubing, less the usual problems associated with handling a bulb and capillary installation. We have talked about the operation and application of various pneumatic thermostats. After device identification, the next item of concern to the service technician is the calibration of these devices. To help simplify this process, we have put together a kit containing all the adapter fittings and instructions for calibrating Robert Shaw pneumatic thermostats. Let's discuss the specific steps involved in calibrating a pneumatic thermostat. First of all, a minimum of 15 psig of main air pressure is required for the thermostat to be able to deliver a 15 psig branch line pressure. Check for a minimum of 15 psig on the main at the thermostat. Insert a gauge and adapter into the branch pressure tap on the thermostat, then move the set point adjustment all the way up or down, depending on whether it is a direct or reverse acting thermostat. Check the branch pressure on the gauge. If it does not reach at least 15 psig, remove the thermostat from the wall, pull the main air line from the back of the thermostat, and check its pressure. If you do not get a minimum 15 psig reading on the main, then go to the pressure reducing station and check its setting. If its output is set for 20 to 25 psig, look for leaks in the system. Now, measure the ambient temperature in the space the thermostat is controlling. This temperature must be measured at the thermostat to accurately indicate the temperature being sensed by the bimetal element. Set the thermostat set point to match the ambient temperature measured in the previous step. This is the reference point the thermostat will be calibrated to. Insert the gauge adapters so that the branch line output of the thermostat can be measured. Take care not to touch or breathe on the bimetal, or the sense temperature readings will be inaccurate. If the branch pressure is not 9 psig, use a 1/16 inch hex calibration wrench to turn the calibration screw until the branch line pressure indicates 9 psig. The thermostat is now calibrated. The set point adjustment may be set to the desired temperature. Remove the gauge adapter and replace the cover. If at any time the throttling range is changed, the thermostat must be recalibrated. There are situations where a controller may be calibrated to some pressure other than 9 psig. It may be calibrated to the midpoint of the spring range of a valve or damper actuator, or to a point between two spring ranges when two devices are controlled by one controller. This concludes the calibration procedure for the single pressure thermostat. Take this opportunity to stop the tape and answer the questions on this section in your study guide. You may want to review some or all of the material on this tape before proceeding on to the next section. Now we will discuss the operation and calibration of the dual pressure thermostats. As mentioned earlier in the program, dual pressure thermostats come in two types, day-night and summer-winter. This example of a typical dual pressure system will illustrate the piping needed. A dual pressure system requires two different air pressures supplied to the thermostats, each used for a different mode of operation. It is necessary to use two pressure-reducing valves set for different operating pressures. Set one for 13 to 16 psig. Set the other between 18 and 25 psig. The specific pressure settings will depend on the control manufacturer's recommendations. The lower pressure is nominally supplied to a summer-winter thermostat when the demand calls for cooling and the system needs to be switched to the summer cycle. A higher pressure is supplied to the thermostat when the demand calls for heating and the system is to be switched to the winter cycle. In day-night applications, the lower pressure is generally used in the day cycle and the higher pressure for night cycle operation. The two main air signals from the pressure-reducing valves are supplied to a three-way air valve before going to the thermostat. This three-way valve is switched, either manually or automatically, to provide the appropriate air pressure to the thermostats in the system. The day-night thermostat is designed for applications requiring two different temperature set points to accommodate varying occupancy demands. This application is most often found in office buildings and schools. The day-night thermostat has two bimetals, both with the same direct or reverse action. Each has a separate set point adjustment so that a setup or set back function can be provided. When the main air pressure is 15 to 17 psig, the day bimetal controls the thermostat's branch line output pressure. The set point for the daytime operation is set by the thumb wheel, the same as the single pressure thermostats. When 21 to 25 psig is supplied to the main air line, the night bimetal controls the branch line output. The night set point adjustment is made here under the cover in the lower left corner of the thermostat. Using a calibration tool, turn the night set point scale until the night set point dial indicates the desired nighttime temperature. For example, a school may want its classrooms to be 72 degrees during the day because of classes, but at night, when the classrooms are unoccupied, they need only 60-degree space temperature. Changing the main air pressure to the day-night thermostats in the classrooms will allow them to set back or set up the temperature in the classrooms during the unoccupied hours. Some models of day-night thermostats have a local indexing feature. This is a lever on the thermostat that allows an individual thermostat to be changed back to the day cycle temperature setting, while other thermostats in the system continue operating on the night cycle setting. This feature is especially useful in meeting rooms or classrooms that may be used at night. A thermostat that has been indexed to the day cycle can be manually reset to the night cycle by returning the lever to its original position. Or it can be left in the day cycle and will automatically reset itself when the main air pressure returns to the day cycle pressure. To calibrate the day set point, position the day set point thumb wheel to match the ambient temperature. Set the main air supply pressure to 15 psig. Insert a branch tap adapter and gauge in the branch tap. Adjust the day calibration screw as necessary until the gauge reads 9 psig. To calibrate the night set point, increase the main air pressure to 25 psig. Position the night set point dial to the ambient temperature. If it does not read correctly, it can be adjusted by turning the calibration screw either clockwise to increase the reading or counterclockwise to decrease the reading until the dial rests on the stop. Continue rotating the screw in the scale a small amount, then turn the screw back to read 9 psig. Read the scale. It should read ambient temperature within 1 degree Fahrenheit. It may take a few tries to accomplish this calibration. Using the calibration wrench, rotate the calibration screw until the dial indicates the desired night cycle set point. The Robert Shaw day-night thermostats are factory calibrated to switch from day to night operation between 17 and 21 psig main air. This setting matches existing Robert Shaw systems, so no switching adjustment should be necessary. If this device is to be used on a competitive dual pressure system, it may be necessary to make a switching adjustment. The switchover adjustment should be done on a test bench where a variable main air supply is available. It is also necessary to read the branch line pressure while making the switching adjustment. The sequence of adjustment varies slightly depending upon the model thermostat used. Here we will go through the sequence of adjustments for the direct acting model. The complete calibration procedure for all day-night thermostat models can be found in the 2214 series datasheet. First, set the main air supply of the thermostat to the desired switchover point. For example, if the system's operating pressures are 13 psig for day and 18 psig for night, the desired switchover pressure would be between 15 and 16 psig. Position the day set point adjustment to a setting of 55 degrees Fahrenheit and the night set point dial to 80 degrees Fahrenheit. The branch line pressure gauge or branch pressure tap should be reading approximately the main air pressure being fed to the thermostat. If not, recheck the daytime set point calibration. To lower the switchover point, use the calibration wrench to turn the switching screw, located on the lower right of the thermostat, clockwise 1/8 turn at a time until the branch line pressure falls. The next step is to lower the main air pressure to the desired system day cycle pressure and observe the branch line pressure. The branch line pressure should rise to the main air pressure. Next, raise the main air pressure to the night cycle setting and observe the action of the thermostat for proper function. As the main air pressure is raised past the switchover point, the branch line pressure should drop to 0, then return to main air pressure when the main air is lowered past the switchover point. The calibration of both day and night settings should be rechecked after any adjustment to the changeover set point. As we mentioned earlier, the complete calibration procedure for all day-night thermostat models can be found in the 2214 series datasheet. Now, let's take a look at the summer-winter changeover thermostat. Like the day-night thermostat, the summer-winter model utilizes a dual-pressure main air system. The summer-winter thermostat uses the dual air pressure system for a seasonal changeover of cooling and heating functions. Indexing the summer-winter thermostat from the summer mode, where the output signal is reverse acting, to the winter mode, where the output signal is changed to direct acting, is accomplished by changing the main air pressure from 16 psig in the summer mode to 25 psig in the winter mode. Models are available to operate on slightly different pressures to replace competitive devices. The summer-winter thermostats come in two models: the single bimetal for the same set point, summer and winter, and a dual bimetal to accommodate different set points for summer and winter. This is the single bimetal summer-winter thermostat. Notice that this thermostat has only one bimetal and looks very much like the single pressure models. This is the energy conservation model summer-winter thermostat. Notice it's a dual bimetal model with two set point adjustments. The set point and throttling range adjustments are accomplished with the serrated thumb wheel on the top of the thermostat and the throttling range slide on the bimetal, like the other thermostats previously discussed. The reverse action of the thermostat is calibrated by the reverse acting calibration screw located in the center of the bimetal. The direct action of the thermostat is calibrated by the screw here in the lower left of the thermostat. To calibrate the summer-winter thermostat, install a gauge and branch line tap adapter in the branch tap hole. Measure the ambient temperature with an accurate thermometer. Move the set point adjustment to the measured ambient temperature using the scale cast in the body of the thermostat. Take care not to breathe on or touch the bimetal, or an inaccurate reading will result. Set the main air pressure to 16 psig. Adjust the reverse acting calibration screw using the calibration tool until the branch line gauge reads 12 psig. Raise the main air pressure to 25 psig. Turn the direct acting calibration screw until the gauge reads 12 psig. That is the calibration of the single bimetal summer-winter thermostat. The dual bimetal summer-winter thermostat is calibrated in the same manner, with the exception of the winter set point. Increase the main air pressure to 25 psig. Use the calibration tool to adjust the winter calibration screw until the branch line reads 9 psig. The winter set point dial must read the ambient temperature within 1 degree Fahrenheit. If it does not read correctly, it can be adjusted by turning the calibration screw either clockwise to increase the reading or counterclockwise to decrease the reading until the dial rests on the stop. Continue rotating the screw in the scale a small amount, then turn the screw back to read 9 psig and check the scale. It should read ambient temperature within 1 degree Fahrenheit. It may take more than one try to accomplish this calibration. Take this opportunity to stop the tape and answer the questions on this section in your study guide. You may want to review some or all of the material on this tape before proceeding on to the next section. The next controlling device we will talk about in this section is the pneumatic room humidistat. The pneumatic room humidistat is also a proportioning type device designed to control pneumatic valves or damper actuators on heating or cooling coils, humidifiers, air washers, and other humidifying or dehumidifying equipment to maintain a constant relative humidity. Here is an application drawing of a humidistat controlling both a humidifier and dehumidifier. Notice the spring ranges on the valves. The reverse acting humidistat increases the branch line pressure as the humidity in the space decreases, opening the normally closed 8 to 13 psig valve, allowing steam to flow to the humidifier. As the humidity returns to set point, the branch line pressure returns to 9 psig. As the humidity increases, the branch pressure starts to drop from 9 psig. When it falls to 8 psig, the three-way chilled water valve on the cooling coil opens, allowing water to flow through the normally open port of the valve and through the coil, which cools and dehumidifies the air being delivered to the space. This device uses a highly sensitive hygroscopic nylon ribbon as its sensing element. It is very important that you do not touch the hygroscopic nylon element because oils and acids on your skin will deteriorate the element and affect the accuracy of the device. The humidistat should be mounted securely to a surface that allows free flow of air to the device. Avoid mounting where humidity-producing devices such as coffee pots are located, since this will affect the sensing of true relative humidity. It is also recommended you do not mount the device on an outside wall. If you must, use the insulating backplate. The 2230-018 humidistat is factory set for a 10% throttling range, reverse action, and calibrated for 9 PSIG branch at set point. However, the device may be changed to direct acting if required by the application. To change the action of the humidistat from the factory set reverse action to direct acting, simply rotate the switching screw 10 complete turns counterclockwise. This change should not affect the calibration or throttling range setting. No further adjustments should be necessary. To change the throttling range, install a gauge in the branch line or use a branch adapter in the branch pressure tap. Rotate the cam by adjusting the thumb wheel until the gauge reads 8 to 10 PSIG branch pressure. The relative humidity must be within the range of the humidistat. Loosen the throttling range slide retaining screw and move the throttling range slide to the desired setting on the throttling range scale. Make sure you keep the throttling range slide parallel with the throttling range retaining screw. Tighten this screw to secure the slide. Adjust the direct acting calibration screw to restore an 8 to 10 PSIG branch pressure. The last device to be covered in this section is the airstream temperature controller. Designed primarily as a low-limit thermostat for use in unit ventilators and central fan systems. This controller is a direct-acting, one-pipe, bleed-type device used to modulate a branch line pressure as a result of temperature changes at the sensing element. In this application, the airstream temperature controller is used as a low-temperature limit located downstream of the heating coil. The restrictor in the airline limits the amount of airflow to the downstream devices, the airstream temperature controller, the hot water valve, and the outside air damper. In the event the airstream temperature controller senses a decreasing mixed air temperature approaching the set point, it will begin to bleed off branch line air, allowing the normally open hot water supply valve to open independently of the space thermostat signal. This allows the system to react to a drop in mixed air temperature before the space thermostat has to react to a drop in space temperature. The 2260 controller is shipped with factory settings of 20 degrees Fahrenheit throttling range and 60 degree Fahrenheit set point. Field adjustments are easily made by removing the snap-on cover. The throttling range is adjustable from 10 to 50 degrees Fahrenheit by means of the slide adjustment. Each graduation represents 10 degrees Fahrenheit. The set point adjustment is made on the graduated dial with each graduation equaling 5 degrees Fahrenheit. The temperature range of the device is 40 to 150 degrees Fahrenheit. Two bulb styles are available on the Airstream controller, a 19.5-inch rigid stem and an 8-foot averaging element. A fixed external restrictor is supplied with the unit. When this controller is used as a low limit in a fan system, it is necessary to order an adjustable external restrictor. This restrictor can be adjusted to provide the appropriate amount of air to the control system. To check calibration, measure the ambient temperature at the sensing element and adjust the set point dial to match that temperature. The branch should be 9 PSIG. If not, turn the zero adjustment with a 1/16-inch Allen wrench until the branch pressure returns to 9 PSIG. Now, return the set point adjustment to the desired set point. This concludes the video material for Section 3, Controllers. Take this opportunity to stop the tape and answer the questions on this section in your study guide. You may want to review some or all of the material on this tape before proceeding on to the next section. For more information about the devices discussed here or other tapes covering Robert Shaw